anything about it until now?
Today we're lucky to have Claudia Felser here to talk with us. She is a boss of a lot of people, a Max Planck director in Dresden, Germany. She's an expert of growing new materials where you can tangle up both the electron spins plus the orbital motion to make new topological effects that were discovered really only about 10 or 15 years ago, but turned out to be really quite powerful and strong, allowing you to make topological insulators, chiral materials, things with edge states and zero applied magnetic fields and the like. And her ability to design and grow these materials has made her very popular amongst her collaborators and somebody we appreciate her. She'll tell you about it.
Yeah, thank you very much for the kind introduction, and thank you all for coming. And forgive me that I didn't recognize that I have to give 2 talks, because anyway, I made 2 different talks. And I made a special talk for this audience, which is a little bit based also on my Kavli lecture. So the title is therefore very broad, and you might not find all the references which I gave in my abstract there because I changed the talk. So if you want to even hear more about topological material science, there's another talk of me at 4 o'clock. So this was a little bit, because I thought I'm always talking to the same person. I didn't recognize that I talked to 2 different persons. But statistically, the probability should not be too high to have 1 talk on the same day. Anyway, so I'm happy to be here, and I'm sitting in Lyman in my office is 235, so if somebody wants to talk afterwards with me, you're welcome, because I'm sitting there for 6 months. Okay, so I'm on a sabbatical. Anyway, so I started a little bit with my talk, which I had to give at the Kavli symposium, but I still have extended it and changed it. So if somebody was at the Kavli symposium at the APS meeting, don't leave. But I thought for this applied physicist, it's maybe more interesting because it shows many different applications despite of simply making a quantum computer. So, and it also explains simply that the materials we are working with are not so far away maybe from materials you already know, and it gives you some simple rules. So to learn more about this. And the reason why I had a very complex title, but the title is a nice guideline through my talk. So the title was given by Paul Kenfield. Somebody knows him, maybe he was the chair of the APS meeting, and he gave me the title. It was the Heusler system. So this is a class of materials I want to talk about, and he wanted me to use it as a Lego box. So therefore I had to build up, I bought for 200 euros Legos. Okay, so if somebody has a kit, I have many Legos after my talk. Okay, and to build the states you are interested in. So this was his title he gave to me, and my duty was to make a talk out of this. And I liked it because it helped me very much to make something totally new. This is the second time I give a part of the talk, and the first time to give this talk here, because it gave me a nice guideline. Okay, so I have a little bit of problem here with the slide, but I hope it works out at the end. So there are two celebrations in 2019. One is that we have 150 years of the periodic table, and this makes a nice bridge to my Lego. So my Legos are the periodic table. So I can play with many of the elements of the periodic table to make new materials, and especially new materials in a special structure type. And the structure types are the Heusler compounds, and they have also celebrating also more than 100 years. You can say, oh, she's working on materials which are known since 125 years. Is this really interesting? Anyway, I hope I convince you it's super interesting. So these compounds were discovered by Fritz Heusler 25 years ago. And his family was owning, even much longer, a copper mine. And so the family, what they do with the copper, and still today they do this, they mix copper with manganese and they make thermocouples. And something beyond, but they are mainly working on copper manganese alloys. And since he already was bought 125 years ago, he thought one should do something beyond copper manganese, and he simply took a third element and mixed this together with the copper manganese alloys. And why did this become so famous? The point is that if you would take a permanent magnet on top of these boxes, nothing would happen, because all of these elements are non-magnetic. But the alloy was ferromagnetic at room temperature. So copper 2 manganese aluminum is ferromagnetic at room temperature, and this was the reason why this person became so famous. Okay, and I, in my story, will tell you there are many, many more properties where you, in this class of material, where you can mix elements and you get very unexpected properties. And I will tell you how to find out which are the interesting material. And if you see this crystal structure type, you can also say how boring, it's cubic. So it's a cubic crystal which has more or less 4 FCC lattices which are interpenetrating. And if you see the balls, you could imagine if you only see the green balls and half of the red balls, it reminds you already from the diamond structure in gallium arsenide if you're working on semiconductors. So the color scheme on my periodic table is even related to the ball. So there are two groups of Heusler compounds. One has a composition 1, 1, 1, and one has a composition 2, 1, 1. And the green balls, they are mostly built by non-magnetic metals. The red balls are built by transition metals, and the blue one, 2 by early transition metals. So you simply can see how to make these materials, and the elements are seen here. So you mix elements from all these boxes, and you end up, most of the time it works nicely with this crystal structure. So as I said, the way what we do with the materials, then we grow single crystals, or we do also thin film growth. For some of the compounds, it's really absolutely necessary to make thin film, because we also have collaboration on devices. So therefore, thin films is the way to go. We have more than 200 different single crystals, and we are collaborating with many people, and most of them are topologically interesting. And I will even make the bridge to topology here about these materials. And the thin film growth happens in my lab, so we have some sputtering systems and an MBE machine, and they are all connected via this line here to avoid to interrupt the vacuum. Okay,
now I come to the third part. You maybe remember vaguely the title was the Heusler compound, the Lego box. This was the periodic table I already explained to you. And now I simply took a Hamiltonian so to show you how we design the materials. If somebody comes with a Hamiltonian and says, can you make, for example, skyrmions or antiskyrmions? So antiskyrmions and skyrmions are very popular nowadays because they have interesting spin structures and they can be arranged in different ways. And these are real space topological materials, so it's different from the topological insulators, but there might be a bridge between real space and reciprocal space topological materials. And you can have them in different symmetries, and this was a prediction by Bogdanov and co-workers. So you can have Bloch skyrmions and Néel skyrmions, and the anti-skyrmions is a mixture between Bloch and Néel skyrmions. And Bloch skyrmions were already discovered in some chiral structures. I will talk tonight about this. At 4 o'clock, they are made by B20, so chiral structures host these Bloch skyrmions. There are already known Néel skyrmion system, but there was no anti-skyrmion were not yet seen. So it was the question. So in the paper, Bogdanov already said you should find it in tetragonal compounds which have a D to D symmetry. This we know, but to host that the material hosts skyrmion, you have to fulfill certain conditions which are nicely described in this Hamiltonian. So you have to have a magnetic material with a certain exchange, Heisenberg exchange, then you need spin-orbit coupling, Jaruzinski-Maria exchange, you need a magnetocrystalline anisotropy, and you might use the dipole-dipole interaction to create this antiskyrmions. So I want to create antiskyrmions. So you don't have to understand now the details of my Hamiltonian because this will be the guidelines for my whole talk. Okay, so why is this maybe eventually interesting? And this should move here, but it doesn't move. So because, so people, even Samsung now, are collaborating with Stuart Parking on the so-called racetrack memory. So this should be moving domain walls. And since skyrmions are even easier to move than the domain wall, so you need much smaller current, people are interested in skyrmions for using them to move domain walls. But then you have to really control them, also their size, etc. Okay. So now I come back to the Heusler compounds and tell you, so the structure is quite easy, so simple, because we can have diamond or silicon, so we know silicon has a diamond structure. It's a very popular semiconductor, but the disadvantage of the element semiconductors is that the band gap is fixed, so you your tuning possibilities are limited, but it's much easier to make them very controlled and very clean. So, but nowadays people even use gallium arsenide, for example, because then they have more tuning possibilities, gallium nitride, etc., for the band gap. So this is nothing else than a binary version of the diamond structure. And then you can say, as a material scientist, it's smart now to think, I can tune things with 2 elements, why not going to 3 elements? And these are the so-called half-Heusler compounds. They are, if you see, here we have 2 FCC lattices interpenetrating the red and the green balls, and here we have 3, the red, the green, and the blue balls, and here we have a second lattice of red balls. The interesting thing is we can have many, many more combination of elements. You simply can do some statistics, you know, and then you can imagine that with 1 element, I only have this possibility here, you know, 4 possibilities. Tin already makes trouble. So with 2 elements, I have more, and with 3, I have even more, and so on. But I want to tell you very easy how it works. For this, I went back and found a very nice other periodic table in the internet, which is from the University of Wisconsin-Madison, and it's even for school education, okay? So it tells you simply why I said silicon is a semiconductor, but we have 2 silicon in the unit cell because 2 green atoms. So, and the good thing is silicon is in group 4, so it has 4 electrons, and 2 of them has 8 electrons, and from the viewpoint of chemistry, 8 electrons, the compounds are quite happy, everybody knows this. And now you can imagine if we have gallium arsenide, we have gallium and arsenic, you see also this fits nicely, 3 and 5. So it's again 8 valence electrons, it's a stable compound, and therefore we have 3 5 and 2, 6 equal to 8 semiconductors. Now you can imagine we can do the same with 3 elements. So we have to, again, have the stable configuration, which is 8. So we get, for example, 1 from lithium. Lithium is in group 1, you see it here. And magnesium is 2, and we stay with arsenic. So it's simple, you know. Now you can make this ternary compound, and the band gap is comparable to gallium arsenide, slightly larger in this compound. So you say, what is so exciting? Why is Claudia so excited about this? So every first-class student, primary school student can do this. The nice thing is, you see the Heuslers, you can use even a lot of transition metals. And transition metal makes material scientists much more excited because we can make magnetic materials and we can do much more. So we can simply say, why not taking the d electrons into account? And we know here we have the full shell of the d electrons if we have 10 d electrons. So exactly we do this, we have 10, 6 s electrons, 6p are 8, plus 10 d electrons are 18. So we can make a semiconductor like zirconium, nickel, tin. 3 metals, mix them together, they are semiconductor. So I can tell you this, but I should prove it. And indeed, just recently we started to prove it because we thought we should convince the people really that what we tell you is true, because this compound is a very popular thermoelectric material. You might have read about this, and if you do the density functional theory calculation, you see here the valence band, the conduction band, and the band gap is 0.5. So we have grown high-quality crystals from this material, and indeed in Ingelrisser photo emission, I hope you can see it. So you see the band gap is slightly larger, what you expect, because density functional theory is not always underestimates the band gap. So we have more or less what we have in the binary semiconductors. We have the sp3 bonding states by the band gap from the anti state, and here additionally we have the 10d. So, but this is for itself interesting, but half the EV band gap is not so surprising. But what has surprised me even more is like a prediction and a realization of Alex Sunger groups. They made tantalum, iridium, germanium, and they are quite metallic. Tantalum, iridium, strange elements, and they have a 2 EV band gap. So it's yellow powder. So who would believe if you mix tantalum? I didn't believe it, you know, until I made it by myself, and Bob Carver made it too, because he didn't believe it too. Okay, anyway, good. So now I want to come the tool topology. Nowadays, we try to understand everything through the viewpoint of topology. And I think there's many, many more to come. So far, we only have seen the tip of the iceberg. So it's very simple. So we stole this idea from mathematics or physics. So because it's even a simple concept. So if you have a ball, there's no hole, the genius is 0, because there's a 0 hole. If I have a donut, the genius is 1, because I have a hole. So if I have 2 holes, I have a genius 2, and if I have 3 holes, I have a genius of 3. So I can go shopping and find German, we call this Berliner or Pfannkuchen. You can have donuts and pretzel. You can even have real life things with topology. Okay, so how can we transfer this into the electronic structure? So we have semiconductors which have a valence band and a conduction band and a band gap, and the band gap depends from the bonding strength between the atoms. If the bonding strength is strong, we have a large band gap, like gallium nitride. If the bonding strength becomes weaker, we have a smaller band gap, and we even can have an overlap between the conduction band and the valence band. So, and if we have an overlap, we can have this crossing points in the band structure. It's more semi-metal. And depending from the symmetry of the bands, or in our case, if we have heavy elements, so this crossing can open up because it can become a forbidden crossing. And in case of heavy elements, the spin is not a good quantum number. So spin-orbit coupling then helps us to open up a band gap and make, again, a semiconductor, which has a band gap. But now our electronic structure has a little bit of the conduction band in the valence band and a little bit of the valence band in the conduction band. And this is exactly what we expect and looking for if we look for topological insulators. Because now our electronic structure of a trivial semiconductor looks like a donut, and the electronic structure of a topological semiconductor looks like a Möbius stripe. So we cannot transform a donut into a Möbius stripe. They have different topology, so we need a scissor, and therefore they are interesting. And since the whole vacuum, the surrounding, all insulators are probably topological, trivial, so, and if my crystal is a topological insulator, it's topological, it has this kind of band structure. So at the surface of this crystal must develop a singularity and a metallic surface state, and the surface state has a special structure. It looks like a Dirac cone, which you know from graphene, and spin and momentum is locked. So this surface state, this metallic surface state is very protected because the spin and the momentum is locked, so you cannot destroy them. And you can imagine if I simply put water on the surface of my topological insulator, I destroy the surface. But I don't destroy the surface state, because the surface state goes simply more into the bulk, because the surface state is a bulk property. It's not a property of the surface, it's really a bulk property. So it simply moves inside until you destroy the whole crystal. It will exist until you destroy the whole crystal. So topological insulators became famous with the prediction of Shushen Zhang and Bernevik et al. So they looked for mercury telluride because they looked for a binary semiconductor which has heavy element, which is quite obvious after they looked for bismuth, and they found that there's no element which has really the topological band structure. They went to 2 elements. After one, not successful, they went to 2 elements, and they looked for mercury telluride, and they found that in mercury telluride, indeed, the s electron is below the valence, so the s electrons in the trivial cadmium telluride, for example, in the trivial semiconductor, is on top, above the Fermi level, which separates the conduction and the valence band, and then it comes in mercury telluride below. But since here we exchange p bands against an s band, we have one problem in mercury telluride. We have the Fermi energy just in the valence band, so we have not really an insulator. Anyway, so to explain this topological insulators, this is a very nice example. And at the end, they had to make a quantum Weyl structure to combine the properties of both to make really an insulator. But I don't want to talk so much about this. But here, it's a nice example where you see the s electrons come below the Fermi energy. So now you can imagine what they predicted with 2 elements, you can also do with 3 elements. Nothing surprising. So you can have many compounds which have the electronic structure of cadmium telluride, but you can have also many compounds which have the electronic structure of mercury telluride. You simply rename this. So now you have scandium nickel antimony, which is a trivial insulator with a wide band gap, and you can have lanthanum platinum bismuth, which is a topological insulator which has an inverted band gap. So, and then you can do opposite, since this is a semi-metal, you still see the surface state, it's just between the gamma 8 and gamma 6 band, and at the end we want to make devices, I will show this, but you see here, you see the Engel-Resort photoemission data really, which shows the Dirac cone-like band structure. Okay, so why should you go with 3 elements if you can live with 2 elements? Because you might gain something additional. Because the Heusler compounds, the ternary semiconductors, they are also superconductors. And the crystal structure of the semiconductors is non-centrosymmetric, so all the physicists are quite excited about this ternary superconductors because it might be unconventional superconductor. And in 2013, in a collaboration with Aaron Kapitolnik from Stanford, he measured even the Kerr rotation, and this can show whether something is unconventional or not. Okay, anyway, why I am excited about this, because we took then the single crystals and made some squits out of this in a collaboration with other people, because it's the advantage of the single crystals, the quality is better than still of ours in films. And so how did we do this? We simply took the single crystal and we grow some aluminum silicon on top of the single crystal. We took advantage first of the natural oxidation barrier, and later we even have made a tunnel barrier in between, and then we made this little squid, and we could see the superconducting transition of lanthanum platinum bismuth and the superconducting transition of aluminum silicon, and we were even able to see Fraunhofer pattern, but this is something which we want to continue in the future, eventually with here collaboration. Okay, so I already explained to you how to make now this compound simply by counting electrons. We can easily make ternary semiconductors, and we maybe can add additional properties in this class of material, like here I showed simply superconductivity, but instead of lanthanum we can have manganese here, or some rare earths which are magnetic, and the manganese compounds have even TCs above room temperature far away, so you can make it magnetic. So, but still we want to make magnetic materials, and we start now therefore now to look how we can tune the Heisenberg exchange in this material, and for this we need compounds which have 3D transition metals to play with magnetization. But we simply can increase increasing the number of electrons exchange interaction, so we can make this material. So therefore we take the full Heusler compounds. So with the 4 interplanetary Z, X2, Y, Z. And here you see the greens, I already told you these are the same as in the half Heuslers. They are non-magnetic metals. But now we play with the d electrons. The blues are on the position of the blues. This is the early transition metal. And the reds can be all on the position of the red atoms. They are the late transition metals. And here we have an example like iron 2, vanadium, aluminium. And in the full Heusler, since we have 3 different transition metals, we have the magic electron numbers 8. So they can be semiconductors with 8 valence electrons. They can be semiconductors like the half Heuslers with 18 valence electrons. But they can also be semiconducting with 24 electrons if I have 3 transition metals. And this is the case here. So we have a compound which has 50% iron, vanadium and aluminium. So 50% iron, so we count the electrons, there are 24, so they are a nice semiconductor. So we have a compound which has 50% iron and it's not magnetic. So it's the contrary from the Heusler compound, it's non-magnetic because it's a semiconductor. So the electronic structure I draw in a simple sketch here. So we have 12 electrons in one spin direction, 12 in the other spin direction. They cancel out this non-magnetic semiconductor, and it has indeed a nice band gap. Okay, so how can we make now magnets out of this? Very easy. We take more than 24 valence electrons. So we take more than 24 valence electrons and we put them only in one spin direction. So we end up what we call a half metallic ferromagnet. So it's magnetic in one spin direction and has a gap in the other spin direction. So one example is, for example, cobalt 2, manganese, gallium. Cobalt has 9 valence electrons, manganese has 7, gallium has 3. In total, we have 28 valence electrons. So we have 12 for one spin direction, and then the rest, 12 plus a 4 in the other spin direction. So if I measure now the magnetization of this compound, it's exactly 4 μ. But it's really attractive also for spintronic application. Now you can imagine, because at the Fermi energy, there where the transport place, we only have one kind of spin. So electrons with one spin, and this is very interesting if you want to make spin electronics, spintronics. I always say this is the reason why Stuart Parking married me, okay? So because I have Heuslers. So Stuart is very famous for spintronic. Okay, good. After he was convinced. Now you can do it with a series of compounds here. I don't want to make exercise of counting electrons with you, but you can imagine for 25 electrons we measure 1 μ. With 28 valence electrons we measure 4 μ. We did this already. And with 30 we measure 6 μ because we have a difference to the 24 of 6. And this is exactly the experimental data. So this is a magnetization measurement which I did for this compound. And since they're all lying on this line, they have an electronic structure like this. And the nice thing is, because at the end, I can tell you, and this I would like to do eventually here, I want to make anomalous Hall effect on material, and I will tell you why I think eventually it's possible. But you see, this material, since I increase the exchange by moving one spin versus the exchange, okay? And this, there's a simple approximation how we can calculate the Curie temperature. This compound, increase the number of valence electron, I increase also the Curie temperature. And because I increase the exchange, I increase the Curie temperature. So I show you now, with this I already have, hopefully you convinced that I can play with the exchange. And you see, if you want to do application, so the Curie temperatures are quite high, you know, they are 1200 Kelvin. So if you want to have room temperature application, these are maybe the compounds you have to go with. So then you can ask yourself, do we really have an electronic structure like this? Do we have 100% spin polarization? For this we made photoemission investigation, spin polarized photoemission investigation, and here you see this is a Fermi energy, and this is 100%. You see cobalt 2 manganese silicon was investigated, it's nearly 100% temperature. So this is what you need at room temperature. Okay, so why I'm so excited and why, so I started a very nice collaboration with IBM, then IBM was sold to Hitachi, so therefore I have a slide from Hitachi. But so now I'm working with Intel, you know, everybody says everybody here. Where we're working for RETAD and MRAM, etc. for this, for Spintronic application. Anyway, so I hope I convinced you how to increase the, or play with the exchange, Heisenberg exchange in this Heusler compound by changing the number of valence electrons. Next step, Jalujinsky-Moria. So this is a term which comes in if your materials have spin-orbit coupling, so if they become heavier. But one of the conditions is also that there is no inversion symmetry in the material, so you play with the topology. So this is the next step which I want to tell you how to do this. Good, no inversion symmetry topology. Okay, so for this we have to remember what is the, I already told you, we can have, if we have a conduction band, two bands overlapping, we have an area of overlapping here in three-dimensional, it's even a nodal line. So on my plot you only saw overlapping points, but if you see it in three-dimensional, you have a so-called nodal line. Nodal line compounds are quite popular nowadays. And depending from the spin-orbit coupling and the symmetry of the crystal, so we can have very different situations. We can have compounds where the nodal line is protected if there's a symmetry plane. We can have compounds which open up a full band gap. So this is the topological insulators, which I already explained to you. And we can have compounds where we have only partially gap opening in this compound. So these are so-called Dirac semimetals or Weyl semimetals, which became very popular recently. So this Weyl semimetals and the Dirac semimetals, they have in common that you have this linear dispersion and you have these exciting properties like you find in graphene. So the properties which you find in Weyl semimetals and Dirac semimetals are very similar to graphene. Weyl semimetals are even more interesting because if you have a Dirac cone, so this Dirac cone is degenerated twice. So if you would simply think you can strain your graphene, what you cannot do because chemistry doesn't allow you, really, so you would split this Dirac cone into two Y points. And the interesting thing of the Y points is they have chirality. And I like chirality. I don't talk about this now, but I really like chirality. So you have a chirality in the electronic structure. So which is here symbolized by this. So there is a chirality in the electronic structure, and Weyl semimetal called Weyl semimetal after Weyl because he solved the Dirac equation and he predicted this chirality. And there's even, if you go to Wikipedia, it might explain the origin of the universe. Okay, so because of the special solution and the chirality. But it's interesting. I don't want to talk so much about, since I'm now already talking about magnetic materials, about the consequences of Weyl metals. There are many, but one interesting fact is that because we break time reversal symmetry in every ferromagnet, every crossing point in every ferromagnet is a Weyl. So I think this is not really investigated this is new stuff because people didn't care about topology and magnetic material. But here you nicely can see every crossing point, so there must be many, many more magnetic materials out there which are interesting. So nobody has investigated because one condition is breaking time reversal symmetry, and all the ferromagnets are white. So this was recognized then in 2016 by Andre Bernevik and others, and you can imagine since these Heuslers are half-metallic ferromagnet, so the bands around the Fermi energy are not so crowded. This is for both spin direction because spin is not a good quantum number if you do fully relativistic calculation. But you see nicely around the Fermi energy, here's the zero energy, you see only crossing points. So this made these people quite exciting in the cobalt 2 titanium tin compound. But since we're working on Heusler since 100 years, nearly, so we immediately recognized, we saw these crossing points before in several of the Heusler compounds, and we found very strange properties which we couldn't explain. So we found, for example, a giant anomalous Hall effect in some of the Heusler compounds, and this was exactly the Heusler compounds which had crossing points close to the Fermi energy. And the interesting thing is, at this time, we did Barry curvature calculation already. This is not done by many people. But we found that at this time, people thought simply, so the anomalous Hall effect scales with the magnetization. If I have a small moment, I have a small anomalous Hall effect. If I have large moment, I have large anomalous Hall effect. Every deviation was explained by some extrinsic effect based on disorder and so on. At this time, we recognized in the magnetic materials, and especially in the Heusler compound, it's not true. So you really see that these crossing points play a role. So this is a Weyl point, so we could show this is a very beautiful Weyl point in these materials. And if you do a systematic investigation, you will see that it doesn't scale with magnetization. So always if you have this Weyl point, that you have a large anomalous Hall effect. So because in these compounds, if you see this is a cubic compound, it's therefore ABC is same. So we have nodal lines in all the directions, so overlapping areas between the bands around the Fermi energy. And so if you apply now a magnetic field, so you can turn these nodal lines into Weyl points, so you have quite a lot of Weyl points in this compound. And this explains the anomalous Hall effect. So this is the anomalous Hall effect. So you do a Hall measurement, but different from silicon, where you see more or less in the first approximation a straight line. If you have a magnetic material, you have this jump. And the size of the jump tells you whether you have a giant anomalous Hall effect or a small anomalous Hall effect. You see already classical properties which people are measuring since long time are reflecting topological properties. It was simply not known. So now we see simply things through different eyes. And what is surprising here, if you calculated the anomalous Hall angle, so proportional to the Hall conductivity, you see the value becomes already 12%. If this would be 100%, it would be the quantum anomalous Hall effect. So this is a super high value and the highest value which was measured up to then, you know. So this might be, and this is a material which has a Curie temperature of 1000 K. Okay. So then you can say, yeah, Claudia, she can tell us everything. She sees nodal lines and so on. So as I explained to you, you need a magnetic field to see the Weyl points, but you see the nodal lines even without a magnetic field. And this is what Hassan's group did in Princeton. So he asked us for thin films and single crystals, and he wanted to investigate exactly this electronic structure. And this is the DFT predicted electronic structure in this compound, and this is a measured electronic structure. And for this nodal line compound, they predicted the theory, very strange surface state, this drum head surface state. Anyway, so Topology became very excited about Heusler compound, and he showed nicely the nodal line in this compound, and he also showed the drums head surface state in this material. So it's really nice because angular photo emission is like photographing the electronic structure. You know, there's a prediction, and then you make the material, and then somebody takes a photograph, and it's exactly like the predicted one. So this made us very happy. Okay, so, but despite of the giant anomalous Hall effect, we know, since we do now this Barry curvature design of materials since some time, we know every compound which has a giant anomalous Hall effect has also a giant Nernst effect. a giant anomalous Lorentz effect. So the idea was, can we maybe make new materials for energy conversion? Because if we have a Y point, this is a toy model calculation from my group, so Noki, one PhD student, did this. So simply he looked, so the Berry curvature, if we have a crossing point in the band structure or nodal line, we get spikes in the Berry curvature. So then if we calculate the anomalous Hall effect, you see the anomalous Hall effect is spiked. So it's very high. So there's we don't expect any linear behavior, which people thought for a long time. But also the anomalous Nernst effect, which is the first derivation of the anomalous Hall effect, shows a nice a high behavior. So why not doing the measurement? Okay, and this is exactly what we did. So until then, we didn't do Nernst measurement, but the only difference to Nernst to Hall is simply instead of a voltage gradient, we apply a thermal gradient in the material and we measure the properties here. You see nicely the Nernst effect versus the magnetic field. So you apply also magnetic field, so it's similar to Seebeck, but you apply magnetic field in this material, and you see it looks like a hysteresis in a magnetic. And the calculation was already surprising because my theoretician told me it's 6. And so far, compounds were only known up to 1 for the Nernst effect here, a microvolt per Kelvin. So I was already surprised, but then the measurement showed even also a very large value. And here you see the Nernst effect versus the temperature. It's up to 300, it really goes nearly 8, and it would go up to the 800 or 1000 Kelvin of the compound. So we expect at 800 Kelvin, it's probably 10. Compare it to known compounds, and this is taken from, I think, a paper from Nagosa. So where the people always thought the Nernst effect goes with the magnetization. This is the way they plot the thing. So they simply magnetization versus Nernst effect. You see there is a kind of linear behavior, but very often people compare the same compound and change the magnetization in the compound by making this order and blah, blah, blah. But you see the values of our compound, we have now another compound, is much larger. It's an order of magnitude larger because of the Berry curvature, because of the crossing points and the Berry curvature. Now you can imagine simply going to other compounds, oxide, etc., would make sense. There's another example, I maybe talk at the end if I have time. Manganese 3 tin, it has, it's an antiferromagnet, it has also a large Nernst effect. You see, it's really related to the topological properties, so they maybe even change the way we have seen normal transport properties. So now what you can imagine, we do a comprehensive database, so we did high throughput calculation of all the Heuslers to find even better materials for higher Nernst effect. And the same you can do for the spin-Hall effect, coming back only, this is also possible, Berry curvature design, because it's in non-magnetic wire semimetals, you can do the same. Why I want to show you the slides is simply, in the next few slides I explain you that this Berry curvature is very much related also to the symmetry. So as I gave you already a few rules of thumb to estimate which Heusler compounds are interesting. So this is another nice rule of thumb, which are the symmetries, why Heuslers are good. Maybe perovskites are good for Nernst effect, giant Nernst effect, because you need high symmetry. Because here is simply we investigated all the non-magnetic compounds in the crystallographic database. And many compounds, and Hall effect, also giant. Minus Hall effect. So now I want to play, still I didn't tell you about topology. You can say she got lost on the way, she wanted to talk about topology. So now I explained to you how to do Berry curvature design, and now I want to simply show you how easily the symmetry can totally change the properties. So same elements, same whatever magnetic moment, but you can have a different properties. So because the half Heuslers, I already told you, are non-centrosymmetric, therefore the superconductivity might be interesting. So the full Heuslers are centrosymmetric, but we can also make a lattice with 4 FCC lattices, which is non-centrosymmetric. So we have to do it if we want to compare this, because here we simply remove the inversion symmetry and the mirror plane. So we want to turn a donut into a half donut, which is then trivial, like a pancake, okay? So this is the next message, and this is how we do it, okay? So we take a compound which has 2 μBor, but I could also take cobalt 2 manganese gallium, but it has more μBor because I want to exactly compare 2 compounds which have the same saturation magnetization, that the people who believe in anomalous Hall effect and magnetization cannot claim I'm wrong. So I take the same compound with 2 valence electrons above 24, so with 2 μBor. So one has a mirror plane here, and one has no mirror plane here because I removed the inversion symmetry. Now, I calculate the Berry curvature, and you already see a difference. Because I told you, so here the Berry curvature, since the crystal structure is very high symmetric, the reciprocal space Berry curvature has to be also high symmetric, no surprise. If I remove one mirror plane here, this mirror plane, I allow the Berry curvature to have different signs. It's still large, but it has different signs. So in total, it becomes 0. So what we see here is the same magnetization, but one compound has a giant jump. It has a giant anomalous Hall effect, and one compound has no jump. Because I made the same compound, same magnetic moment, I removed one mirror plane, and I have no anomalous Hall effect. And this is how topology works, you know, so you get totally new properties which are depending from the topology of the electronic structure. So I turned a donut into a pancake. So what happens here? Because you have seen this figure on the paper of Andrei Bernevik and Hassan from Princeton with the crossing point. But in the moment then, these points are protected by mirror symmetry. So the Y points are protected by mirror symmetry. If I remove the mirror symmetry, they are not longer protected. They become a forbidden crossing, and a nice band gap opens up. The second message is also, which I like this result, is not only that I remove the Y points, which are more interesting than no Y points, okay? But I make a metal into a semiconductor, but it tells me also there must be a way to turn this into a quantum anomalous Hall effect, because by changing, so I can change this electronic structure into a semiconducting electronic structure. Anyway, okay, second point. So I hope I have explained to you Jagodzinski-Maria and how I can play with topology. Now, third term is magnetocrystalline anisotropy. Okay, so how can I play with the magnetocrystalline anisotropy? I have a cubic compound, A, B, C are the same. So for having a magnetocrystalline anisotropy, I need a crystal anisotropy. So I have to make the crystal anisotropic, so I have to change one of the lattice constants. And this here I can do by straining the material, so making simply a tetragonal material, or I strain it along the 1-1-1 direction, I make a hexagonal compound. Anyway, so this is also very interesting, and this is not that we are working on this now. We're working on this for a long time, because there was a prediction of that MRAM will be shipped, and to get Heuslers into MRAM, you have to have tetragonal Heusler compound, because people like Stuart were looking for materials which have high perpendicular anisotropy. So, and here to remind you, spin-Hall effect-based MRAM is maybe the next generation. So looking for a spin-Hall effect and Berry curvature maybe makes also sense, even beyond quantum computing. So I think this week Samsung announced that they shipped MRAM as a mass production, not yet with Heuslers, but IBM and Stuart are working on this. But also the tetragonal Heuslers with magnetocrystalline anisotropy, people working for various free hard magnets and other stuff on this, okay? So you can do this if you go, for example, manganese 3 gallium, it has a tetragonal structure, and the manganese 2 cobalt gallium, you saw already, has a cubic structure, and here in thin films you nicely can show how it works. So the manganese 3 gallium has a tetragonal structure. You see it's out of plane magnetized. You see a nice hysteresis here, and even if you put more cobalt in, you reduce the moment, you get a giant hysteresis of 4 Tesla in this compound, and then it becomes soft magnetic. If there's more cobalt, it becomes cubic. So we can tune the magnetocrystalline anisotropy. We even can calculate here in density functional theory, so whether we have in-plane or out-of-plane or in-plane magnetization in these materials, and we did it for many of the manganese 2 Heusler compounds with 3D elements, 4D and 5D, and you see the out-of-plane magnetization is easy to achieve if you go to heavy elements. And I remind you, so to have a large Jaruzinski-Maria, heavy elements are also good. So luckily there's no contradiction out of plane magnetization and Jaruzinski-Maria. We are in a lucky situation. And if you look for compounds here close to this transition point, they might have non-collinear spin structure, which is a complex magnetic phase diagram, is also a precondition to make this skyrmions. So we increase the spin orbit coupling. We increase the magnetocrystalline anisotropy, and then more or less we also increase the spin orbit coupling because you saw that the magnetocrystalline anisotropy is very large if you have heavy elements, so there's no contradiction between Jaruzinski-Maria and magnetocrystalline anisotropy. And this was the result. We made a compound which is non-collinear, has a complex phase diagram. I don't want to discuss this in detail because we already are later. But what was interesting in this compound, we could grow very nice in films of this material, which is at the end nice if you want to make devices. And we saw this nice topological Hall effect, which is the signature in the Hall effect for skyrmions. And this was the first pictures which we got. This is a long time ago. But at the end, we focused on another compound which has even a heavier element like platinum. So it has also very complex phase diagram. Here's temperature, and you see a spin reorientation transition, non-collinear spin structure at low temperature, a collinear at higher temperature, and so on. So which makes it really a nice candidate material for skyrmions. So we have very nice single crystal, which is very difficult to grow because these compounds are all, this was very impossible from the rhodium compound because the cubic and the tetragonal phase diagram is very often close to each other. People know this, so working on magnetocaloric in these materials. So, but we were able to grow the single crystals and we see nice non-collinear spin structure. So now what is missing, so we see now this is the right material, and if you then see, this is a Lorentz stem. It shows you really the anti-skyrmion structure. If you see, the anti-skyrmion structure looks more like a d orbital, while the skyrmion structure looks more like an s orbital. And these are the in-plane magnetization, and you see a nice hexagonal lattice here of skyrmions. Everybody can see it. So this is here extended, but you know, it's Lorentz stem. Anyway, and there's an interesting phase diagram. So in the range where we can do Lorentz stem, which shows that there is some room temperature application possible. Okay, so now we have still the last term here, the dipole-dipole interaction, and this is only a few slides. You see the dipole-dipole interaction in the shape anisotropy we can tune in this material by making these micro wedges of this material, and this is a way to even, what I want to show you, change the size of the skyrmions by the size and the thickness eventually of thin films. This is still here on the micro scale because the detection limit of the Lorentz stem is like 100 nanometers. So if you want to go below 100 nanometers, this is here the big question mark because we cannot do it easily. But you see with the wedge, you can even change the size of the skyrmions and the collinear, the domains of the non-collinear spin structures. So I think I skipped this part because I'm running out of time. And I hope I have showed you that simply by taking into account a part of our work, the Heusler compound, that you can play a lot. And I only talked to you a little bit about the topological insulators, the magnetic Weyl metals, and the anti-skyrmions, that you can play nicely with many tuning parameters. And this is because you can very easily substitute atoms, and you have a broad variety of composition which you can use to play with the topological properties to have insulators, semiconductors, Weyl and Dirac. Semiconductors, we can have antiferromagnetic, and compensated ferromagnetic compound, non-collinear spin structure, in and out of plane, and so on, and from isotropic to anisotropic, and we can have also phase transitions between the different states. And with this, I thank you for your attention, and this is simply many more properties which were already discovered in the Heusler compound, and I'm sure there's much more to come, even especially in the context of quantum and quantum devices, and I thank you for your attention.
That's impressive talk. Anything? Questions?
Yeah, that's a question. How do you grow this material? Do they fall in the right place magically? Or is it under high temperature, high pressure? What kind of growth method?
Very, very good question. So the good news is, since they are like semiconductors and compound, they are not fully disordered. They are not alloys. At the beginning, people mentioned that they were allowed. I would say the topological properties are much less sensitive to disorders and other properties, seems to be. You know, it's surprising. You know, how can you have zero? So we more or less grow them so far by sputtering and by simply growing in flux or something. So, but I'm sure if we want to make quantum devices, we have to do MBE growth. And people like Lorenz Mohlenkamp, they're already growing them by a molecular beam ataxy. So if we want to have really quantum anomalous Hall effect, I think we really have to grow them by MBE. But very good question.
My question was kind of related. I was wondering if some of the compounds you grow, if you know them to be both stable, or like what metrics of chemical or thermodynamic kind of stability do you use before you decide to grow something?
So one thing is always a phase diagram. We have to have a look. So not all the possibilities which are theoretically possible from the statistics work. In this sense, yes, we have to look for the phase diagram. We can look also for DFT calculation, whether the compound are stable. But disorder is an issue, but it's like in some composition, it's more an issue than in others. So I think this is also a little bit like intuition. You know, some are easier to grow than others, I have to say, yes.
What was the conclusion from the squid measurement that you showed?
Yeah, because we are not the expert with the Fraunhofer pattern, so we really need more work to do. So maybe in collaboration with Amir and so on. We simply wanted to see, can we build a squid from single crystals, because the single crystals are better ordered than sputtered films so far. Or we have to do MBE growth, what we are now doing with Lorenz Mohlenkamp. Okay.
But the
So,
driving is like, to test if it's a P wave or D wave?
yeah, exactly. If it's non-conventional superconductivity, and if we see some deviation in the Shapiro peaks or something like that.
Is it possible, like in the growth, to do similar stuff? Like in ITC, they do this like different orientation, like 3 different orientation, and looked on vortices in the middle.
Yeah, but if you take the single crystal, you can cut the crystal with different orientation.
So it's not possible to go like different orientation.
You can grow thin films in different orientation, but so far we did the single crystals, and then it's even more easy because we simply cut a certain surface, you know. Yeah. So here we simply wanted to see. So in thin films we still have problems. The TC is 1 Kelvin to see the TC, okay. And because you really have to have well-ordered samples. But in single crystal, we get quite good ordered samples, and therefore we thought we should check whether we can use the single crystal as a basis to make this grid by focus ion beam, you know. And it seems to be we see both superconducting gap and we see Fraunhofer pattern, so we can use this as a starting point, yes. But then we can do it. Here we simply took, I think, the 1, 0, 0 plane, but we can take different orientation too.
Other questions? Okay, if not, let's thank Claudia again. And again, you're here on sabbatical for 6 months and 235 Lyman?
Yeah.
Great.
235, yeah, Lyman. So.
Right.